Hi, this is my presentation on the convection heat transfer coefficient. So this is the rate of heat transfer between a surface and the surrounding fluid, and it's not a material property, meaning it's determined by the fluid properties such as mass, density, and like the geometry of the cup and also temperature. And a high H value means that there's efficient heat transfer going on, so heat is leaving the system quicker and there's less heat retained. And a low H value means that heat is slower to transfer out and heat is kept in the system. In my experiment, I'm going to be using Newton's law of cooling. I'm also like equation. I'm also been using the thermal time constant equation and plugging that in for the tau value. This allows me to insert H into Newton's law of cooling so I can see what the H value is for my specific system um, when temperature is changing. So for my assumptions, I'm going to assume lumped capacitance so that there's no temperature gradient and that there's uniform temperature throughout. And this just allows me to, I don't have to track where heat is or how much heat is left. I can assume that there's uniform heat. Additionally, I assume constant physical properties, so constant mass, density, geometry of the cup, and fluid used. And I also assume uniform and constant H. So the H value I calculate, I'm assuming to be the only H value in the system. I'm assuming that convection is the only method of heat transfer occurring. And I'm also assuming that the fluid, surrounding fluid temperature, so the room temperature is also constant. My initial condition is that at time equals zero, the temperature is the initial temperature. And as my boundary condition is that as time increases and approaches infinity, it's soon going to approach room temperature, which is T infinity. So the materials I use are a glass cup and insulated cup, which I'm comparing the H values for, and I'm also using a scale, meat thermometer, boiling water, and a stopwatch. And I'm measuring temperature changes at 1 minute increments as temperature is going to decrease. And I'm expecting to see that as temperature decreases, that temperature will decrease as time increases, as heat should be leaving the system. I'm also going to be expecting to see that the insulated cup retains more heat. So here are my initial values of mass, and note here that the mass in the insulated cup is higher than the mass in the glass cup. And the dimensions of the cups will help me calculate characteristic length. So first I put the boiling water in the cup, like I record the mass, and then I measure the increments. It's important to note that I don't want the thermometer tip to be touching the surfaces of the cup. I want it to be in the fluid of the water because I want it to just be measuring the fluid temperature and not like the surface temperature. That's something to keep note of. So this data collection is only here to show that the glass cup reaches room temperature a lot quicker than the insulated cup. And this is also shown here. And you can see here that the insulated cup values stay above the glass cup values the whole time. So this means that the insulated cup retains more heat for a longer period of time, and it's at a higher temperature throughout. This indicates a lower H value, that it should have a lower H value, the insulated cup. And also you can notice that they're losing heat at nearly the same rate. The curves are very similar, and this is likely because they're in similar conditions. Both cups have open tops and they're on the same counter, so they might be losing heat the same way. So to solve for H, first I solve for volume using the dimensions, and then I solve for characteristic length. And I don't use the long cylinder assumption because I don't really think that length is that much greater than radius, so instead I just do V over A. And here I simplify Newton's law of cooling. So I take out A over V because that's just 1 over characteristic length. And I get rid of the exponential and I just isolate H. So to calculate H for the glass cup, I'm going to use temperature at 10 minutes. And this is because I thought of maybe using temperature at closer to 50 minutes or closer towards the end, but that's not really indicative of heat transfer that's going on because the system is a lot closer to room temperature. So not as much heat is being transferred out. Whereas at T equals 10, you can see that it's right in the middle of decreasing temperature, which means that heat is being transferred out of the system. So I think that for the convection coefficient to make it calculated accurately, using a temperature and time at which heat is actually being removed from the system, like more consistently, is better. So that's why I chose to use T equals 10. So I plug that in, the temperature value, 10 minutes, I convert it to seconds. I get H equals 53.7 watts per meter squared Kelvin. And on the right, it's just like my units canceling out because there's a lot of variables going on. And I calculate H also using T equals 10, like time equals 10, just to make sure that it's all uniform. And when I compare the H values, I see that the H of the insulated cup is higher than the H of the glass cup. But from the graph and from what we know about insulated cups, it should be H insulated should be lower than H glass. And this is likely because the insulated cup has a higher mass of water than the glass cup. So the insulated cup has more mass of water, so it has a larger rho VC, but it still has a very similar cooling rate to the glass cup, like we saw in the graph. So this means that the equation can only be balanced if H is larger, so H must compensate. And like conceptually, what this means is that more water is cooling in the insulated cup at the same speed as less water in the glass cup. So more heat has to be pulled out in order for this to happen. So that's why there's a higher H. So the discrepancy in mass is probably why. And also, it's incorrect to assume uniform H because heat is also losing from the top and from the bottom, and I can't really account for that. Additionally, liquid is also evaporating, which is removing mass, which means that our assumption of constant uniform mass is likely incorrect as mass is changing a little bit. So when I compare to literature, I see that my calculated H values are a lot higher than the literature H values found in the textbook. And this discrepancy can be due to like an open tops of both cups, so heat is flowing out and heat is also transferring away because of the contact between the bottom of the cup and the counter. And it makes sense that my values are higher because my experiment and my system is less secure. So heat is being transferred away quicker as opposed to being retained in the system, which is why my values are a lot higher. Thank you. Oh, to remedy this, I would, in my future experiment, I'd probably put a lid on top. I'd probably like have it not on such a um surface. Thank you.